All right, we've got our recording started, so I'm going to go ahead and get us fired up. I hope everybody had a relaxing spring break, or I guess as relaxing as it could be given the circumstances. I'm going to get right into our topic today. What we're going to be doing is covering shear design, and I've got an example that we're going to do that's going to be very similar to one that we did before break, but given that it's been a couple of weeks since we've talked about this, I figure it's a good idea to go ahead and review it. Just some very brief announcements, just to make sure everybody's on the same page. All of your attendance grades are up to date. All of your homework grades are up to date, homeworks 1 through 5, and all of those associated solutions should be posted, as well as your exam 1 grade with the corrections. So everything up until now is graded and current. Now, I've got the chat here up. If you have any questions throughout the lecture, you can either type them in the chat, or if anybody's calling in or using a microphone, feel free to ask the question throughout the lecture. Just do me a favor and keep the microphone muted until then, just so that we don't have a bunch of feedback during the lecture. Now, if you've had a chance to look at Blackboard, you'll notice that I've done a couple of, I don't want to say changes, but I've added some stuff to Blackboard. There's a new folder called Online Live Stream Lectures and New Course Operation for COVID-19. Everything from here on out, homeworks, exams, lecture notes, are all going to be in that folder. So that way everybody's looking at the same thing. And so with that, I'm just going to get started. I want to first off go through our procedure for shear design. We've talked about this before, and we've seen this in our previous notes. What I've done here with these slides and the slides that you're going to see throughout the rest of the semester is, instead of using my old lecture notes, what I'm going to do is I'm going to sort of retool them in this format. And the idea is I'm trimming all the fat out of the notes and just keeping them direct, short and sweet, and to the point. So for instance, today's lecture really only has like 6 slides, and that's going to be very consistent from here on out. I'm going to keep it short, sweet, and to the point. And then after the lecture, I'll talk about the homework assignment that I've got prepared for you. And it's the same idea, short, sweet, and to the point. So with that, let's get into shear design. So the first step that you always have is to construct the shear diagram. As you can see, I have an image of a shear diagram right here on the bottom right. What I have here is a shear diagram for just a simply supported beam for a uniformly distributed load. During our next lecture, we'll talk about what we have if we have a scenario where we have different loading, like concentrated loads and whatnot. But for today, we're just going to keep it simple. When you construct the shear diagram, you need to look at 3 regions. You need to define the region where stirrups are required. You need to define the region where the concrete carries the shear. That's that region 2. That's where there's enough VVC to supply the load, but you still have to provide stirrups there. And then there's the region where no stirrups are needed at all. And so when you construct the shear diagram, you need 3 points. You need VU star, which is the shear at a distance D away from the support. And then you also need to know the X coordinates at VVC and half of VVC. And just so everybody has it right here, I have the equations down below. VC is 2 lambda BWD squared of FC prime. And then don't forget phi is 0.75. One other item is, when you go to Blackboard, you will see that these lecture notes are already posted, and I'll have the lecture notes posted before each lecture as well as I build them. Okay, next, what you need to do is compute 2 design S values. Now, this procedure is formatted a little differently than what was in the previous notes, but it's all the same work. I just tried to make it as direct and straightforward as possible for you as the students. So what you'll need to do is compute 2 S values, your S required, which is the required stirrup spacing at VU star, and then S max, which is the maximum spacing. S required is a pretty simple plug and chug formula. You can see that above. S max is the minimum of S max 1 and S max 2. S max 1 and S max 2 are what are listed below. Now, I wanted to throw this note here on the bottom of the slide. If you notice, that if you go back to the old notes, you won't find this note here in the slides. I put this here because I wanted to make it, again, as simple for you as possible. There are scenarios where S max could be smaller than S required. I even gave homework and exam problems like this where this happened, and I'm trying not to do that here. I'm just trying to keep it simple and straightforward for you. Whenever S max is smaller than S required, what that just means is that the beam doesn't have much load on it. It's very lightly loaded. And if that happens, you just use S max for your design. So I don't want you to find yourself in a scenario where you're doing a problem and you compute these two values and S max is smaller and you're like, oh, what do I do? You just use the S max. So there's that. Now, let's assume that S required is smaller than S max, which is what I would say is a very typical scenario. That's going to be typical with our problem here. This step would be only required if S required is smaller than S max, but what you need to do is determine when you can begin starting to use S max. So you'll compute the shear capacity using S max. So that you start off by computing VS and then you compute VVN. And then you consult the shear diagram, those equations that you derive for the shear diagram, to figure out where that value occurs along the shear diagram. And don't worry if I'm throwing a lot of details at you. A, I know we've seen a lot of this stuff before, but B, don't worry, we're going to have a very straightforward start to finish example with all of this here in a little bit. So what you then do is consult the shear diagram to figure out where VVN occurs along the beam. And this is one of the reasons why you identify region 1 and region 2, because that should be in either region 1 or region 2, most likely in region 1, right before region 2 starts. And last, you need to actually design it to lay out the stirrups. So your first stirrup is usually placed at half of your S required from the support. A very common value is to place your first stirrup 2 inches from the support, and we're pretty much going to use that for the entirety of the semester. So we'll always place our first stirrup 2 inches from the support. And if you have a typical design where S required is less than S max, put your first stirrup down, which would be 2 inches from the support, and then place your first set of stirrups at S required and keep using S required until you hit the X value from step 3, and then use S max until the end, and the end being wherever X was at half of VVC, because remember, after half of VVC, you don't need to place stirrups. The concrete can carry the shear by itself. Last, if S required is greater than S max and all you have to use is S max, just place your first stirrup and just use S max until the end. It's pretty simple. The only other point I would make is a common design strategy is to keep your S values at multiples of 2 inches. So whenever you're designing, use like S equals 2 inches or 4 inches or 6 inches or 8 inches. The reason why folks do that is it makes the math pretty easy when you're designing, because it's simple to it's pretty simple to figure out the multiples and the increments, since everything's in multiples of 2, 4, 6, and 8. When you start throwing in like S values of 5 and 9 or a 9 and 7 and things like that, it can sometimes be a little difficult to keep track of. It usually makes it easier on the contractors. And also, it usually doesn't result in unnecessary extra stirrups. You might throw maybe 1 or 2 extra stirrups in the beam if you were to use multiples of 2 inches, but usually it's not that big of a deal. Again, the goal is to use as few stirrups as possible, but to keep the pattern simple. Now, I'm going to try and steer us away from this last point in our homeworks and exams to come, but I just wanted to mention it. If you have an S required and an S max that are really, really far apart, maybe consider throwing another stirrup spacing in the middle. So if you had like an S required of 6 inches and an S max of say 18 inches, that you might have like a really, really tight grouping of stirrups and then a really, really wide grouping of stirrups. It might be a good idea to throw another increment in the middle, maybe like, I don't know, S equals 12 inches. That might be a situation where you can really reduce the number of stirrups. So you just repeat step 3 using S equals 12 inches and figure out where you can start using that spacing. Again, keep in mind the goal is to use as few stirrups as possible, but you got to keep the pattern simple and easy to follow. And that's it for the notes. Again, I'm trying to keep the notes short and to the point. And I just want to get right into a design example. So I want to take a second and digest what we've got going on this slide. We're going to lay out stirrups for this beam. First off, if you look at the bottom sort of left, you can see I've got the beam dimensioned. It's a 14-inch wide beam. The depth is 24 inches, and I've got 4 number 9s in the beam, although that really doesn't matter. The flexural reinforcement doesn't matter for design purposes. All we really care about when we're designing for shear is B and D. Now, if you look over here on the right, this is going to be something I'm trying to do throughout our online lectures, is I really want to make it easy for us to get through the problem. So a lot of the background work, if you will, I've kind of already done for you. So for example, if you look at the top, this beam is subjected to 3 kips per foot of dead load and 5 kips per foot of live load. So I just went ahead and factored it for you, and that comes out to 11.6 because I figure everybody can do that. I also figure everybody can compute the support reactions, so just WL over 2. So 11.6 kips per foot times 16 foot over 2, that comes out to 92.8 kips. And I figure up until now, everybody can draw the shear diagram. So I went ahead and plotted the shear diagram here. I also went ahead and included the equation for the shear diagram as well, and I'm pretty sure everybody can derive that. Now, I'm getting ready to start the example here in a second, but if anybody has any questions, again, please throw them in the chat, or you can respond via audio. But I hope up until now everybody's okay with me just including these introductory calcs, because I figure it's pretty straightforward. If everybody is good, what I'm going to do is I'm going to stop sharing this PowerPoint, and then I'm going to turn on my my OneNote so I can begin these calculations. So give me 1 second. I believe this is the screen. Okay. So everybody should see a OneNote, like a blank white notebook with Shear Design distributed load on the screen. Okay, what I'm going to do is get my pen ready. Okay. Pull the chat up so I can see what's going on there. Give me 1 second. Okay. So can everybody see everybody should be able to see the whiteboard with the pen and whatnot. So we're going to go ahead and get into to this example. So I'm going to start off with step 1, which is to construct the shear diagram. Okay. So let's identify just a couple of base values just to make sure everybody's clear on some things. So we have a beam. We know that B is 14 inches. We know that D is 24 inches. We know that FC prime is 4 KSI. And the problem told us that we were dealing with normal weight concrete. So that tells us that our lambda value is 1. And we're also dealing with regular grade 60 rebar. So that means that this is 60 KSI. Okay. So another thing that we knew off the bat is we knew that we were dealing with number 3 U-shaped stirrups. So remember, the area of a number 3 is 0.11 square inches. So because they're number 3 and they're U-shaped stirrups, this is 0.22 square inches. Okay. Now, let's start off with our structural analysis. And like I said, for this problem, I went ahead and told you that the equation for the shear was just the reaction minus Wx. So the way that I'm going to write that is this, is I'm going to say that the shear, which is going to be in kips, is going to be 92.8, because that was the reaction that was given, minus 11.6x. But what I'm also going to write here is that this is in feet. In other words, remember the 11.6, that's the distributed load, that's in kips per foot. So your X value is in feet and your shear comes out in kips. That's just sort of a shorthand way of me identifying the units for the problem. Lastly, I'm going to go ahead and solve this equation for X. So if I solve this for X, I'm going to get, what do I do? So I say the V kip minus 92.8. Let me redo that. Over negative 11.6. So those are two expressions that I will use later when plotting my shear diagram. Now, is this legible? Is everybody able to read this? Could somebody let me know in the chat? Awesome. Good. Wonderful. Okay. Now, in order to plot the shear diagram, we need three quantities. We need VU star, which we could go ahead and get VU star now, but I'm going to wait until later. But because we need to plot VU star, but we also need to know the X quantity at phi VC and half of phi VC. So we might as well start computing those values now. So let's look at our concrete capacity. I'm going to scroll this up a little bit. So first off, V sub C. So if you recall, that's 2 lambda BWD square root of FC prime. Okay, so let's plug and chug that. So 2, we're dealing with normal weight concrete, so this is 1. For this beam, BW, remember that's the web width, but since we're dealing with a rectangular beam, we just use B. So that is 14 inches. D is 24 inches. And then the square root of FC prime. Remember, FC prime is 4 KSI, but we always put in 4,000. Remember, put in PSI, get out PSI. Now, if you say 2 times 1 times 14 times 24 times the square root of 4,000, that comes out to be 42,501. Now, this is a shear, so it's a force. So the units in this case are pounds. And they're pounds because you put in PSI, you get out PSI, but it's PSI times inches and times inches. So PSI times square inches, the square inches cancel and you get pounds. So VC is 42,501 pounds, or VC is 42.501 kips. And so with that, we can compute phi VC. Now, phi VC is phi. Now, phi for shear is always 0.75. And VC is 42.501 kips. And then when you plug and chug this, this comes out to be 31.88 kips. Okay. And again, if I'm going too fast, or if you ever have any questions, please don't hesitate to type a question in chat and interrupt me. I've got no problem with that at all. Okay. Oh, something popped up on my. Okay. Now, next we need half of phi VC. So half of phi VC is just half of this, 31.88 kips, which comes out to be 15.94 kips. And so with that, we can compute our three important values for the plot. So sorry. Okay. So the first is VU star. So what VU star is, remember that's the VU at X equals D. Now remember, that's the value that we use for design. That's where we start our design. Now let me go ahead and remind everybody what our equations are. We have V kip is 92.8 minus 11.6 X in feet, and X in feet is VU minus, or sorry, V in kips, sorry. V in kips minus 92.8 over minus 11.6. Again, these are both the same equation, just one is solved for V and one is solved for X. So I'm solving for a shear here in this case. I'm going to use the first equation. So this is going to be 92.8 minus 11.6. Now the D for this expression, D is for this beam is 24 inches, but this is why I have the equation written this way. This is my quantity for X, 24 inches, but the equation says I have to plug in X in feet. So I need to do a unit conversion. So I need to say 1 per 12 inches. So I need to remember to do that whenever I'm plotting these out. So I need to make sure that I'm plugging my X values in feet and my shears and kips accordingly. So when this is all said and done, you will get, so plug and chug, 92.8 minus 11.6 times 24 over 12. That comes out to be 69.60 kips. Okay, so that's our first value. Second value is the X at phi So now I use the second equation, and so I just say phi minus 92.8 over negative 11.6, and phi was 31.88. I'll just leave that as is, minus 92.8 over negative 11.6. Right. Now, when you plug and chug this, you're going to get, so just take these values, plug them into your calculator, you're going to get 5.25. Now, remember, we're solving for X, and our expression states that this is in feet. So this is 5.25 feet, or 63.03 inches. Okay. Ultimately, when we're designing stirrups, our X distances in inches would make a little more sense, because that's how our stirrup increments are laid out. But just make sure that you're cognizant of what units are going in and what units are going out to a given expression. Last, we have X at half of phi. So the exact same equation, just instead of 31.88, just use 15.94. Okay, so 15.4 minus 92.8 and all that divided by negative 11.6. That comes out to 6.63 feet, or 79.51 inches. Okay. All right. Like I said, if you have any questions, please type them out in the chat. I can always scroll back up and down and go through something. Okay, so now we can plot our shear diagram, and it's pretty straightforward. Remember, the shear diagram for a beam like this just looks, like that, something like that. And this is 92.8, negative 92.8. All I'm going to do is sort of magnify that first region, the region on one side of the span, and just identify all the values that I previously plotted. So I'm just going to take that and plot it a little bit bigger. So this is X in inches. This is shear in kips. And then our shear diagram looks, let's see, what we got. Sorry. So, oh goodness, got stuff popping up here. Hold on. There we go. Okay. So shear diagram goes like this, but I'm going to draw that first part dashed. So this is 92.8 kips. That's the reaction. But then we don't use the absolute maximum shear for design. We use the shear at VU star. So this is VU star, which is 69.6 kips. So forgive me, my scale is probably a little off here, but that really doesn't matter. What matters most is the actual values for the design. So again, the shear diagram goes all the way up to 92.8, but we're just not using that. Now over here at the very, very end, that's the midspan. So I'll call this sort of the center line of the beam, or the midspan. That would be this point right here. So this X value, so if you remember, the beam itself is, what is it? The beam is 16 foot long. So this right here is, let me use red here. This is X equals 8 foot, or 96 inches, because that's where midspan is. Remember, the beam is 16 foot long, so that's 8 foot. Now this is VU star. This occurs right here at X equals 24 inches, because that's D. And lastly, we have two other shear terms that we computed. We have this term and this term. This is phi VC, which is 31.88. And this is half of phi VC, which is 15.94. Okay. So lastly, what we can do is identify where those occurred on the beam. Phi VC occurred at X equals 63.03 inches. This is X equals 79.51 inches. And so let's see, what do we got? So this is region 1. Everywhere where the shear is greater than phi VC, this is where we desperately need stirrups for capacity. This is region 2. And when you do your design, you should always check region 2 to make sure that in region 2 you're always using S max. You'll probably use S max in a little bit of region 1 as well, but definitely you'll be using S max in region 2. And region 3, you shouldn't really be using any stirrups at all. You'll use stirrup. You might have a stirrup maybe bleed over into region 3, but by and large, you shouldn't need any stirrups at all there. Okay. So fortunately, that is the longest part of the example. And when you see your homework assignment that I've given you, I'll go ahead and tell you that I've actually already done that whole part for you. But I'll pull that up here in a little bit when we get closer to the end of the lecture. So that's step 1. I'm going to assume everybody's good with that. If anybody, again, has any questions, type them out in the chat. Otherwise, I'm just going to jump right into step 2. So I have a feeling that's going to happen a lot. Me accidentally bringing up my on-screen keyboard. I apologize for that. Okay, so step 2, what we're going to do is compute 2 S values for design. All right. So the first one we're going to compute is S required. S required is VU star on the bottom minus PVC on the bottom, and then on the top, phi, AV, FYT, and then D. And again, there's nothing really special about this equation. All this is just taking the PVC equation, the PVS equation, saying PVS plus PVC has to equal PVN, setting PVN equal to VU star, and solving for S. So that's all there is here. And so this is what is my stirrup spacing required at that maximum level of shear. So on the top, we have 0.75. Then we have 0.22. We have 60 KSI. And then D was 24 inches. Oh, sorry about that. And then VU star was 69.6 kips minus 31.88. Okay. Now, when you plug and chug all of that, first off, this is a stirrup spacing. So your units will come out to be in inches. So for instance, on the top, you've got 0.22 square inches, and then the KSI, so that comes out in kips. And then the kips cancel with the kips on the bottom, so the only thing you're left with is inches. Now, when you chug this out, you will get a value of 6.3 inches. Okay, I have a question. Let me see. Where did the 0.22 square inches come from? Okay, great, great question. Let me see. I'm going to see if I can pull something up. Give me 1 second. That's a great question. All right. Okay, so let me try something. Okay, give me 1 second. I'm going to stop sharing this. Then I'm going to share an application. Okay, so what I have here is the rebar chart. So this is looking at various reinforcing bar sizes. And if you look at the area of a number 3, if you look here, has an area of 0.11 square inches. Okay, and so that's remember, if you have a number 3 bar, the diameter of a number 3 is 3/8, so pi over 4d squared. The diameter being 3/8, so that'll come out to be 0.11 square inches. So the area of a number 3 bar is 0.11 square inches. Now, if you then look at the problem, so let me go back to the problem. So the problem stated that we were going to have number 3 U-shaped stirrups. So what that means is, let me see if I can drag this over to my other monitor here. Give me 1 second. Apologies. Okay, so I have number 3 U-shaped stirrups. So what the stirrups look like is sort of like that. And so whenever you're looking at your cracked region in shear, you're sort of asking yourself, if I crack the beam like that, how many bars do I go through? And in this case, I go through 1, 2. So my AV is going to be 2 times the area of whatever stirrup I'm using, in this case the number 3, so 2 times 0.11 or 0.22 square inches. So that's why we're using 0.22. No problem at all. No problem at all. Okay, now let me see if I can go back to, give me 1 second. So stop sharing. Hold on. Okay. All right. Everybody should see the screen now. So let's get back here. So we had S required. So S required came out to be 6.3 inches. Now we're not going to tell a contractor to use 6.3 inches. We're going to tell them to use S equals 6 inches. Okay. You always round down. Rounding down is the more conservative option because that means a larger capacity. If you need 6.3, you're going to use 6. You're not going to round up. Now S max is always the minimum of S max 1 and S max 2. So S max 1 is the minimum of D over 2 or 24 inches. Okay. And D over 2, or D was 24 inches. So 24 inches over 2 or 24 inches. So that came out to be 12 inches. And then S max 2, the formula for S max 2 is kind of long, but it's not hard. So B times the maximum of 0.75 times the square root of FC prime, or 50 PSI. And this is AV FYT. Now, I need to do this calculation off to the side because I didn't do this. Let me see. So 0.75 times the square root of 4,000. I'll put that over here. So 0.75 times the square root of FC prime is 0.75 times the square root of 4,000 PSI. When you plug and chug that, that comes out to be 47.4 PSI. So what we're going to do here is we're just going to use BW times the maximum of either that or 50. So we're going to use 50. So BW was 14 inches. This is 50 PSI. AV is 0.22 square inches. And then now when you're using FY, remember FY is 50 or 60 KSI, but this has PSI, so make sure you express this as 60,000 PSI. Okay, don't forget to change your units here. This is a very easy way of tripping up your problem, so don't forget that there. Now, when you plug and chug this, you're going to get 18.86 inches. So we have two options. We have the use of S equals 6 inches. Then we have the minimum of S max 1 or S max 2, which is right here and here. So we're going to use S equals 12 inches. Okay. So step 2 says we needed to compute 2 S values for design. We did, and we have S equals 6 and S equals 12. Now, step 3, we have to figure out where we can start using S equals 12 inches. Okay, so So I'll say compute range for S equals 12 inches. See, we don't need to do this for S equals 6 inches because we know when we're going to start using S equals 6 inches. We're going to start our first stirrup at 2 inches, and then we're going to start using 6 inches right at the beginning. We know when we're going to start using the 6 inches. We don't know when we can start using the 12 inches. That's what we've got to figure out here. And so the way that you do that is you start off and you say, okay, if I use S equals 12 inches, what's the capacity? So we start off with VS. So VS is AV FYT D over S. So 0.22, 60, 24 over 12. And so when you plug and chug, that'll give you 26.4. This is a shear, okay? So the units are in kips. So again, what that's saying is if I use S equals 12 inches, I'm going to get a capacity from the steel of 26.4 kips. And so the entire shear capacity is going to be PVC plus PVS. So that is, now PVC, we already computed that. PVC was 31.88 kips. We don't need to apply phi here because we already did, but we do need to apply phi to this one. So just make sure you're keeping track of proper bookkeeping. You don't need phi for the PVC because you already have it, but you do for this. So 26.4 kips. And plug and chug, and that comes out to be 51.68 kips. And then now what we want to do is we want to consult the shear diagram to figure out where does that value occur on the shear diagram. And if you remember, we had an equation that said that we have V in kips minus 92.8 over negative 11.6. If you remember that, we're going to do the exact same thing here. We're going to use this shear value and plug it into this expression. So X at VVN is 51.68 minus 92.8 over negative 11.6. Now, when you plug and chug, I didn't do the feet one here, so give me 1 second. So that comes out to 3.54 feet or 42.54 inches. Okay. So what this is saying is that we can start our design with 6 inches, and we can keep using 6 inches until we get to this point right here, and then we can start using 12 inches. Now, if you remember in the notes, I said that a good check is that this value should occur either in region 1 or region 2, most likely in region 1, but just before it. So 42.5 inches, if I scroll up a bit, where is that? That's going to be right around, oh, that's going to be right around there. So that's X at VVN. Again, just before, it's either in region 1 or region 2. Most cases it'll be in region 1 just before region 2, and that's exactly what we found here. And so the last thing to do is just do your design. So how does that work? So we'll say layout stirrups. And here's how we do it. We place the first stirrup at 2 inches. And that's just common. That's very typical with shear designs. You always should put your first stirrup either at 2 inches or half of S required. Either one's fine. Next, we're going to use 6-inch spacing until X equals what is that, 42.54 inches. So that's what we just determined. And then we're going to use 12-inch spacing until the end. And the end is going to be 79.51 inches. And that's because that's where X is at. This is the X value at half of PVC. So if you want, you can say this is X at half of PVC. This is the X from step 3, if you want to sort of flow chart that out. So here's how we'll do this. So we'll say 1 stirrup at 2 inches is 2 inches. Then we start placing stirrups at 6 inches. Then we'll place stirrups at 12 inches. So let's see how many spaces that we need. So we need a certain number of increments at 6 inches. So let's see, we've already got to X equals 2. So if we put 1 stirrup at 6 inches, so 2 plus 6 is 8. So that's 1 plus another, that's 8 plus 6 is 14. So you keep going in 6-inch increments, and the idea is to get past this X value here. And so what I'm going to do is I'm just going to go ahead and tell you that ends up being 7, okay? And I'll show you why. Okay, so 7 times 6 is 42. So this gets us to X equals 44 inches. Now, an easy way of seeing why that works is, okay, I used 7 increments. Let's say I used 6. Okay, so 6 times 6 is 36 inches. That would have only got us to X equals 38. That's not far enough. We need one more increment to get us past X equals 42.54. So that's why we have to use 7. Okay, so that's probably the only other thing about shear design that's maybe a little confusing. Last, we need to use 12-inch spacing, and I propose I'll end up using 3, because 3 times 12 is 36 inches, and so if you're at 44 and you go out another 36 inches, that gets you to X equals 80. Again, just imagine if you only did 2 at 12, 80 minus 12, that's what, 66, or sorry, 68, and that's not far enough. So there's your design right there. So that ends up being 11 stirrups all the way to 80 inches. Now remember, that's only to the center line of the beam. Remember, if you scroll up, this shear diagram only goes to the center line. So if you have 11 stirrups on one side of the beam, you need another 11 stirrups on the other side of the beam. So it's actually 22 stirrups total. And that right there, that is your answer. Okay. So that's in a nutshell how shear design is performed. I want to really briefly show you your homework assignment, and I want to show you what I've done to make the homework assignment a lot faster for you. Let me stop the sharing real quick and pull up the homework assignment. I think it's okay. So one of the things that I decided to do for our coronavirus lectures from here on out is I'm changing up the way that I'm doing the homework assignments. Instead of doing a small number of assignments but making them really big, I want to try it and make sure that everybody stays engaged, but at the same time I don't want to just load you down with work. I don't think that's right either. So what I'm going to do is we're going to have these really short sort of mini homework assignments from here on out, and I want to show you that it really shouldn't be a massive amount of time going into the homework assignment. So first off, if you notice, I've given you a homework assignment that is very similar to what we just discussed in class. It's almost pretty much the same problem, just changing a few numbers around. Another thing that I did for you is if you scroll down, you'll see not only have I factored the loads, not only have I factored the reactions, not only have I given you the equation for the shear, but if you go to the next page, you'll see I've even given you the shear diagram. So with all the critical values and distances and shear quantities already computed for you. So again, I wanted to make this as easy on you as possible. I really think that on your own, this assignment shouldn't take more than, I don't know, 15 minutes, maybe a little bit longer, but no much more. So we're going to have this assignment due on Wednesday. If you look, I think it turns on at 11. If you look inside the online, the COVID-19 folder in Blackboard, you'll see this assignment available. Just do the assignment on, some 8.5 by 11 white paper. I'm not even really worried about quad paper anymore. You can just do it on 8.5 by 11. As long as it's legible, that's really all I'm concerned about. And as long as you get that done by Wednesday at 10, you should be good. What we're going to do next time is we're going to take this problem and just ask ourselves, well, what if we had some point loads, some concentrated loads on the beam? How would it change? And then we'll have a similar example. Again, I don't think this homework will be very long. I'm not trying to load you down with work. I want to make it as simple on you as possible. A final note before we close the lecture, I'm going to be holding, I guess, office hours Monday, Wednesday, Friday from 1 to 3, and I'm Tuesday, Thursday from 10 to 12. During that time, I'll be available via Microsoft or via phone, via email. If you want, we can also connect via Microsoft Teams. I will probably set up a Microsoft Teams profile for the class so that you all can contact me via camera if you would like. And we can go through homework problems or any questions that you have moving forward. Let me go to the chat. I don't see any other questions, but question, will the lecture still be posted on YouTube? Yes, my plan is yes. It might take a little bit more time because I have to download them and then post them, unlike the software I was using before. But we are recording this lecture now, and if you go through Blackboard Collaborate Ultra, the recordings will be available there as well. So one way or another, you will have access to the recordings. I'm still going to record the lectures from here on out. Any other super quick questions? All right. Well, since most of you are in steel design, I apologize for this, but we're all going to have to log off and then log on to the steel design lecture here in a second. So if you're not in steel design, I'll see you on Wednesday. And if you are in steel design, I'll see you here in a couple minutes. So that's all I have, everybody. We'll see you next time.